All right, so we're going to look at using trapeziums to estimate the area underneath curves. So we looked a little bit previously at the left endpoint estimate. You can imagine there's such a thing as the right endpoint estimate. They both use rectangles. But you can probably imagine that using a trapezium would be a better way to approximate the area under some curves, and you'll see why that's the case in a second. So I just wanted to jump straight into an example. I think you'll see the logic behind it as we go. So it says using three trapeziums of equal width, estimate the area under the graph of y equals f of x, the x-axis, and the lines x equals pi on 6 and x equals 2 pi on 3. So we've got this function here, f of x equals sine times sine of 2x minus 5 pi on 6 plus 2. Okay, between pi on 6 and 2 pi on 3. And nicely enough, I've got this nicely drawn out for us here. And yeah, our job is to use three trapeziums of equal width to estimate the area under the graph. The first thing we might want to do is we might want to draw those trapeziums in. So, and since it's between pi on 6 and 2 pi on 3, if we split that up into trapeziums of equal width, I think you can work out that they would have a width of pi on 6 each if there's three of them. So let's just draw them in. So there's our first trapezium. There's our next one, and there's our last trapezium. You can see how this might be a better estimate of the area underneath the curve. If I had a, say, right endpoint estimate here, this would be a rectangle and be overestimating it by a lot more. Similarly, if I had a left endpoint estimate, I'd get my rectangle would start down here and come down here. So you can see how a trapezium might be a much better approximation of the area under a curve. And then, so we've also got this part here. This pretty much approximates it perfectly there. And then we've got this part here. So yeah, using trapeziums can be a better approximation. So let's jump into the maths of things. Yeah, let's talk about what the area might be. So this line here, let's just break it down. This A sub T is just talking about the total area. Okay, well, we know since they're equal width and it goes from pi on 6 to 2 pi on 3 that it has to be, they have to have width of pi on 6. So this length here is pi on 6. Okay, and then you're probably wondering where I got this 5 on 4 from. Well, when I think of trapeziums, I just think of them as average rectangles, right? So I can see here the left end point at pi on 6 is at 1. The right end point is at 1.5. And so, yeah, I think of this as a rectangle kind of with an average height in between. So halfway between 1 and 1.5 is 1.25. So that's 5 on 4 as a fraction. If you're not sure why that's the case, 1.25 times 2 is 2.5. And then double it gets you to 5. So a quarter of 5 must be 1.25. Anyway, so we get that situation there. And then similarly with this next rectangle, again, the width is pi on 6. And the average height of this trapezium, this is kind of how I think about it, is between 1.5 and 2.5. So the average height is right there in the middle at 2. And then similarly, the last one has an average height between 2.5 and 3. So that's 2.75, which is 11 on 4. So that's where we sort of get this line. I just jumped straight into it with that sort of theory, understanding what a trapezium is. You can obviously use the area of a trapezium, which is this, but I think this overcomplicates things. If you can think of a trapezium as kind of an average, a rectangle with an average height between the 2 points, I think that helps. Anyway, you'll probably notice that pi on 6 is common in each of this. So if we take pi on 6 out as a factor, we're just going to be left with pi on 6 multiplied by 5 on 4 plus 2 plus 11 on 4. Some simplifications, which I haven't done there, so don't ignore that. All right, anyway, if you add these part up, you get 6. And so pi on 6 times 6 equals pi. So the area, an estimate of the area of three trapeziums underneath this curve is pi. And I actually think this is the exact area. So I think I've done this question where you take the definite integral between some points, and I think the answer is pi. So this is, in this case, it's actually not even an estimate, it's correct. But you can see why it might be an estimate because it might not always get it perfectly correct. But in this case, obviously this area here cancels out with this area here. So this part that underestimates it is cancelled out by this part that overestimates the area. And then if we zoom in, you can probably see there's some area underneath there above and below that trapezium line there. So they cancel that too. So we get the exact area, which is pretty neat. All right, hopefully that clarifies some things.